Hi everyone, welcome to day 3 of the UK OUG conference 2020. Dave will be presenting regarding active session history. Dave is happy to have questions throughout, however, at certain points. So if you have any questions, please do a reaction. I will look out for them, as well as you can type in the chat, and then at the right appropriate time, I will let David know and he can answer those questions. Over to you, David. Thank you very much.
Thank you, and thank you everyone for joining me today. Welcome to part 2 of my session on ASH. If you've worried you missed part 1, I actually did it last year at Brighton, and you can find that on my website, and you can read about some other things on the blog. I'm an independent consultant. I do performance tuning, and I wander around helping people get the most value for money out of their Oracle database. And as a result, things like active session history is I think I spend a lot of time using to analyze what goes on in the database. And so one of my objectives for this session is to help you understand what ASH does and how it works and how to use it. And what I'd like to do is to encourage you to go digging in the ASH data yourself, which is a lot of what you're going to see in this session. Examples curated from real life. Oops. Okay, when I'm being a little bit frivolous, I sometimes say there's really only one question in performance tuning, and that is, how much time did I spend doing what? Now, it's also, I follow that up by saying the only place to measure that is standing behind the user with a stopwatch in your hand. And that's very much the case when you've got distributed systems and you've got app servers. You spend time in your app server and time in your database. And if you saw Toon's presentation the other day, he will have talked about the total response time, app server, network, and database. We're going to focus very much on active session history, which is database time. It's the response of the database only. And quite often, when you're examining a database performance problem, and you've identified what's going on and you say, well, what can I do about it? It's surprisingly often the case is, well, whatever it is that's taking the time, stop doing it. ASH is all about finding out where the time's going. What did you do that's causing your performance problem? And then you have to decide what you do about it. Okay. So the few things we're going to cover today, I hope if we have time. There's some tricks to use the ASH to get more information out. There are some consequences of certain aspects of design we'll talk about, which make ASH a little harder to work with. We'll look at some of the traps that you can fall into where things go wrong and it might mislead you. And we'll look at where you can use ASH to find out some things about the database that it's not immediately obvious that ASH is the tool to answer that. I'm going to do a very brief recap of part 1 because it was a year ago. But really, I want to get into some of these other areas. So ASH has been with us since version 10 of the database. It was principally architected by Graham Wood. Now, Graham has since retired from Oracle to go motorcycling, but he has left behind him a number of presentations, some of which are on Oracle's website, some of which you can watch on YouTube. And if you want to find out how ASH works at a nuts and bolts level, I very much encourage you to watch these. It's an hour well spent. And he worked extensively with, well, John Brezhnovich there worked extensively with Graham, and they're both quite on the list of authors of the patents that were registered for ASH. John very much put the mathematical basis into active session history, and you may have seen a recent presentation of his on the Oracle Groundbreakers tour when he talked about the basics of database time. And some of the following slides have been lovingly ripped off from what these two guys have done. ASH is a sampling technology. Essentially, the database is sampled every second. You look for sessions that are active and you sample them. if they are active at the point where the sample is taken. So here I've got 3 database sessions, and each of them consumed 4.5 seconds of database time. And you will see where they intersect with the samples, and where they intersect with the samples, we collect ASH samples and we record them. And ASH records either 4 or 5 samples, depending on how the sessions fall across the sample points. And we say that those sessions have 4 or 5 seconds of database time as far as ASH has detected it. So it's a sampling technology. It's an approximation to what goes on. You can see that it's off by half a second either way. That approximation becomes more accurate as the number of samples increases. So let's add a few more sessions, and we'll add a few more samples. And so you can look at database activity and you can say, well, there was so much database time in each of these sessions, and you can start to add up the samples at each point in time across the database, and you can say how much database time, how many active sessions were there at this point in time. And I could take those totals across the top and I could draw them as a bar chart, and I get a feel for how much activity there is in the database. Or I could draw them like this, and I assure you that the area didn't change there. And now it starts to look like every monitoring tool that you've ever seen. Particularly, it looks like the top activity graph in Enterprise Manager, which of course is a view of ASH data. So you can start to estimate the amount of activity in your database. And then you can also start to break it down by different attributes or different types of ASH data. So the mathematics behind this is, how much database time is there? Well, it's approximately equal to the duration between the samples multiplied by the number of samples. So because it's 1 sample per second, you count 1 second of database time per sample. So basically it's 1 second for each row you find on $$ active session history, which is the in-memory ASH data. 1 in 10 of those samples are persisted into the AWR repository, so you count 10 seconds for that. So the next stage is to start mining this data yourself. And you start by writing SQL. And all of the SQL starts to look very similar after a while. And I tend to write it like this: select sum of 1 second for each row from $$ active session history, where it's the rows you're interested in, grouped by the attribute you're going to profile by, ordered in descending order of database time. And if it's the persisted data, then I do select sum 10, just to emphasize the 1 second and the 10 second for the in-memory and the persisted data. From Oracle 12.2, there is a new and as yet undocumented column on the ASH data, USECs per row. They use U instead of the Greek letter mu. It's microseconds since the last ASH sample. So you could start to write SQL, which is just sum USECs per row divided by 1 million. And now that's the number of seconds of DB time. What you actually find is it's about 1.02 seconds on average between samples. It drifts a little, it varies from row to row. But for all practical purposes, you can work with 1 and 10 seconds. And of course, if you went from DBA hist active session history, you'll get about 10 million microseconds between the rows. So your SQL now becomes identical depending on which one you query. So ASH is a data warehouse of information about activity on your system. The fact is that there's one row. That row is a fact of 1 second of, or 10 seconds of DB time. But there are lots of attributes in different dimensions. You've got time information. When was the sample taken? You've got information about the session. What's its status? There are a whole load of in flags that will tell you what state it was in, pars, bind, exec, etc. You get information about the wait event, including the wait event parameters. If a session was blocked by another session, you get the information about the blocking session. You can use this like a linked list to go from blocked to blocker and to navigate up the chain of blocked rows. You get information about the application. You'll get program, machine, port. If you have instrumented your application, you will get the module and action. Now, that normally appears on $V session and it gets picked up in a number of places. One of those places is ASH. And now you have application context in your ASH data. I know which part of my application is responsible for this SQL statement that was captured in ASH. That's something that the developer has to put in. It is massively valuable. It's impossible to overemphasize this. A couple other columns, you get client ID and ECID is the execution context ID, which can be useful with Java applications. You get the Java thread ID, and it maps down to the SQL that was submitted by that thread, so you can marry the two up. You get information about the SQL, the execution plan, the line in the plan, whether it's in a transaction, the execution ID. You get information about PGA and TEMP usage. Lots of things that you can slice and dice your data by, and you'll see examples of that coming. You also get an object ID, file ID, block and row number now. This will only be valid for physical file IO operations, operations where file and block is an attribute of the wait event, basically. For all other events, it's actually just left over in the session registers from a previous event. Just so you can use it, you just have to be a little careful with it. Okay, so how might you typically use ASH? Make sure you have a clear idea in your mind about where you're going. In plain English, I often say. When was it you're looking at? What time window? Is it recent or is it historical? Do I want one session? Do I want to look at a group of sessions? Maybe they come from an app server. I might sometimes just group the whole of the database, say, where is my time going in this database? Do I want all of the ASH data? Do I want one event, one SQL ID, perhaps just one plan hash value? Or if I'm looking at blocking sessions, do I need to relate ASH from the holder to the blocker, to the blocked rather? So then you move to starting to form SQL to interrogate the data. The persisted ASH table that underlies DBA hist active sesh history is partitioned by DBID and SnapID. That's just done automatically. Therefore, I always join in the snapshot view so that I can obtain the range of DBIDs and SnapIDs from that. If you simply query the ASH data by time, you will end up scanning all the partitions. So join them by the keys and force it to start with the snapshot view. Sometimes it won't do that on its own, it has to be helped. And you start to write SQL that looks like this. First of all, I'm going to look for the snapshots that intersect with the period of time that I'm interested in. So that roughly matches my snapshots. And then I'm going to do an exact match by time against the sample time on the ASH data itself. And then I'm going to filter it by module. In this case, I'm looking for an application server. So I want all of the sessions, on the ASH for all of the sessions that went through the app server. And I'll get a profile. These SQL statements took this amount of DB time, profile it in descending order of time, work from the top down. So now I know which SQL ID spent how long. To find out what this means, what the SQL ID and the plan hash value actually is, well, you've got to go looking in AWR for that. So let's take this SQL statement, and I would do something like this. I would now select the plan using DBMS plan display AWR and pass that SQL ID and that SQL plan hash value, and I'll get an execution plan. Notice I've used the adaptive keyword. We'll explain the significance of that in a couple of slides. That's if it's coming from AWR. And if it's coming from in-memory, I can do display cursor. And this time I pass it the SQL ID and the cursor ID. Now, you can look at an execution plan and you can get an idea of where the cost is. But sometimes it's not obvious from an execution plan to see where the cost is. So I tend to profile an execution plan by the line ID to say which line is taking the most time. And so now I can see which lines took how much time. And it's very obvious that lines 24 and 25 are the things I need to look at. So now I can go and look at the execution plan and look at lines 24 and 25. And here you are. These two lines are the place that took the most time. This is where I need to start digging. In this case, I've got an index I'm using. I'm full scanning an index inside a nested loop, and I keep, for each row up from my nested loop, I'm then doing a lookup on this transaction table. It may be that other parts of the plan look more expensive, but remember the costs here are the cost estimates from the optimizer, and they may not be right. A number of performance problems occur when those costs part company from reality. But by profiling the ASH time by line, you can find where you actually spent the time. Sometimes I profile by line and by event. So here it's very obvious that line 3 is where we spend all the time, but I can see that some of my time was spent on the physical I/O and some of my time was spent on read by the session. So somebody else is also reading this block hard, and I'm waiting for, and they've asked to read the same block, and now I'm piggybacking their read. So this is a hot block problem. So not only do I see how much time, but I see what kind of event I'm waiting on. Okay, that was the basics. And I did a lot more of that in part 1. Let's dig a little deeper. From Oracle 12, you now get adaptive plans. Basically, Oracle can change its mind midway through about how it's going to approach an execution plan. So here I have one SQL statement, and I've got two different plan hash values. Notice they have the same full plan hash value. Different adaptive plans within the same plan will have the same adaptive plan hash value. Note you've got this column SQL adaptive plan resolved. That's pretty much always going to be 1 unless you are in the middle of the parse. That doesn't actually mean that you have an adaptive plan. But I've got one SQL statement, two plan hash values with the same full plan hash value. So this is the plan. Note it's got 7 lines. And there's a note at the bottom that says, this is an adaptive plan. Great. But I can't see what the plan that it discarded was. What's the other half? Well, I'm going to run DBMS plan with the adaptive plan option. And one of the effects of this is that now the SQL plan line ID in the ASH data will match the line numbers in my profile of the ASH data. So here's my full plan with the adaptive keyword. The note is changed. It now says rows marked with a minus are inactive. So you can see the stats collection operation, which is where Oracle looks at how many rows were actually returned and then makes a decision. And here, what it's done is it's chosen between the hash join and the nested loop. And this is actually probably the most common transition you'll see with adaptive plans. So those lines I faded out, they're not in use. And what I'm left with is the same 7 lines that you saw in the previous execution plan. And here's the other plan. And this is what it swaps between. On this occasion, it said, I'm not going to do hash join. We're going to do nested loop. And you've got lines 1 to 12 and lines here 1 to 10. Let's go back to the profile. And this time I'm going to profile my hash data by plan hash value, full plan hash value, and the plan line ID. And here I get my 2 profiles. And now I've got lines 1 to 12 and lines 1 to 10. And I've got just one sample where plan resolved was 0. So by using the adaptive keyword, the line IDs correspond to the lines in the plan. It was pretty obvious in this case, but in more complicated plans, it may not be obvious to you that the line ID in your ASH data doesn't correspond to the plan, and it might lead you to the wrong place. So I now always use the adaptive keyword from Oracle 12 upwards. It's just hard-coded in there now, and I don't bother. Obviously, if you're back on Oracle 11, you don't have the adaptive keyword, and it will cause DBMSX plan to error. Okay. Literals versus binds. They can be a bit of a headache in ASH. Because if you're using literals, you now have non-shareable SQL. It's a new SQL statement every time. It has to be reparsed. It has a new SQL ID. And it leads us also to talk about histograms and binds. And they exist for diametrically opposed reasons. And you might read Jonathan Lewis's note on the subject. So we use bind variables where we have frequently executed SQL statements, which are doing a usually small, but generally similar amount of work, and we want the same execution plan for them. In these cases, quite often the overhead of SQL optimization is significant as it mounts up over all of the executions. So we want them to share the child cursor. And this is a typical situation for OLTP. It's certainly generally the preferred approach, that you should use bind variables and not literals wherever possible. That should be the default. But there are occasions where the reverse is true, where you've got, typically in batch processes, large and highly variable amounts of work. And these guys need different execution plans depending on the amount of work going on. And where there's a large amount of work, the overhead of SQL optimization isn't particularly significant compared to the execution. And in these cases, histograms may be helpful, and using literal values rather than binds may be preferable, and they will help you to use those histograms. But they come with a couple of consequences. Every SQL statement is a different SQL ID. It has to be parsed afresh, and it creates additional challenges for you when you come to analyze the data in ASH. And there are some techniques you can use to help you. Here's a SQL statement, which is typical of the problem. It actually comes from a PeopleSoft time and labor batch process. It's saying, does the person who approved this time have the security privilege to approve this time and labor exception? And what's going on is they've taken a query, grafted on a security view, and then grafted on the operator ID. But they haven't passed the operator ID as a bind. It's in there as a literal value. So when you come to profile the SQL, what you get is lots and lots of different SQL IDs that all actually produce the same execution plan. Here it's very obvious that it's that one execution plan is where all your time went, but you frequently see more complex situations where that's not the case. Plan hash value is a special case. We'll come back to that. Wouldn't it be good though if I could actually treat all of these guys the same? I could group this statement by force matching signature. And force matching signature is like a SQL ID, it's a hash value of the SQL text after you've converted literal values into bind variables. But I actually prefer grouping by plan hash value. You get differences in the statement sometimes that produce a different force matching signature, but you still get the same execution plan, different numbers of terms in an in clause, adding additional criteria that are not indexed frequently have this effect. If two statements are similar enough that they produce the same plan hash value, then they are likely to experience the same problems and benefit from the same optimizations. So now if I take the same data set and I group by plan hash value, it's very obvious where my time went. The statements that produce that plan hash value, 226, etc., and took 2300 seconds, that's what I need to focus on. Always focus on the thing that took the most time. Now your challenge is, can I find the SQL in the AWR repository? Was it even captured by AWR? And this is the downside. Lots of parsing causes lots of statements to be aged out of the library cache. It may be, but by the time you took your AWR snapshot, that statement wasn't in memory anymore. And it may also be that it's not one of the top end statements, by default top 30 by 5 different sort orders that are captured by AWR. So you may not find it, and you may have to work hard to find a statement that exhibited that plan hash value, and sometimes you won't. All you'll have, the only thing you'll know about a statement is the SQL ID and the plan hash value. It's very frustrating. So what I tend to do is I left out a join to the DBA hist table. So I count the amount of ASH time for all of my SQL IDs, but I also count DB time for statements that I know about. 10 times the count of t.SQL ID. Where I haven't got the statement, it's going to be null, I'll count 0. And then I can use some analytic functions and say, for each plan hash value, I want the statement for which I have the most DB time that I know about. And I get a profile like this. So now I have, for each plan hash value, the statement that took the most time. Now, the top row, you'll see this quite a lot. The top row is plan hash value 0. Lots of things produce plan hash value 0. Calls to PL SQL, insert value statements are all plan hash value 0. So here, I've actually detected 74 different SQL IDs that have got plan hash value 0. And I've only actually captured 480 seconds of DB time out of the 38,000 seconds that were actually sampled by ASH. So I don't know about all of them. The second one is an example of shareable code. It's either shareable code or it was only executed once, but I've got one SQL ID, one that exhibits one plan hash value. But this is the case that we're trying to deal with. This line, plan hash value 189, etc. There were 198 different SQL IDs that exhibited this plan hash value, and SQL ID CXWZ9, etc. That's the one that produced the most DB time for which I know about the SQL ID. Now, in this case, rather unusually, you can see it's 4190 seconds in both columns there, so I actually have every SQL ID, and that's quite unusual. But on this occasion, it's happened. So if I now want to examine this plan hash value, I can get a DBMS DisplayX plan for this SQL ID, and I know I'll find it in the AWR repository. So where your developers have not been using bind variables, this tactic can help you. Okay. ASH and RAC. RAC's become far more common over the years, lots of people using it. It has its own challenges. Each RAC instance is autonomous in terms of how it manages ASH. Each one has its own ASH buffer in its own memory and does its own sampling and runs its own AWR snapshots. That has some consequences. First of all, the sample IDs on the ASH rows do not match. They're not even close. ASH, it's basically a counter. It ticks over as the database runs. You start and stop your RAC instances at different times. They're going to get out of alignment from day one. So you cannot join sample IDs across RAC instances. Not only that, but the ASH samples occur at slightly different times. Sample time isn't going to match. It's a timestamp, so it's by default accurate to a microsecond. The instances are not going to collect their samples at the same time down to the microsecond. So I tend to round them off plus minus 1 or 10 seconds, or match to within half a second, 5 seconds. One thing that does match across instances is snap ID, and that's because AWR, although it's run independently, it runs on a schedule that's common to all of your RAC instances. So you can join across RAC instances by snap ID. So I tend to have this little rounding function. I put it inside my SQL these days rather than create a database object. And I round it off to, in this case, 10 seconds. And then I can group my ASH data within that 10-second sample and whatever else I'm going to group it by. People like using parallelism. Parallelism can be very effective, but it can also be a very brutal way of just burning CPU. You can use ASH to determine whether it's an effective tactic. So you've got information on your ASH data about the session ID and the session of the query coordinator. So you know whether you are in the same parallel operation. If I look at the ratio of elapsed time to DB time, I get my effective parallelism. So here I'm going to count distinct sample times. That gives me my elapsed time, and I'm going to count the number of distinct processes grouped by instance, session, and serial ID, serial number. Grouped by query coordinator as well, and I'm going to take the ratio of those two values. And now I get a profile for each execution of each statement. How many processes did I have, and how many of them were active at any one time? Well, here I've got a parallel 16 statement. I've got 16 producers, 16 consumers, and a query coordinator, but only sort of 4.5 to 5.5 of them are really active. So in this case, I've probably wound the parallelism up too far. Here, I'm getting up to 129 processes, and usually over 100 of them are active at any point in time. Now, this has only lasted 20 to 30 seconds. I've only got 2 or 3 samples. So in fact, what's happening is that some of them are finishing before the first ASH sample goes off. this is actually parallel 128, and it's using it. It's actually very effective use of parallelism. So you can start to see, is my parallelism worth it, or should I tone it down and release CPUs so that other people can use them? PL/SQL. When you call a PL/SQL statement, you have another column called the top level SQL ID, and that's the SQL ID of the PL/SQL call. If there's SQL within it, then you get a different SQL ID, and that's how you can detect recursive SQL. And if I profile by SQL ID and top level SQL ID, you can see which is recursive SQL inside my PL/SQL procedure and which is just ordinary SQL from my application, if it's not using PL/SQL. So for instance, if it's DBMS stats, this might be the SQL inside the PL/SQL. One of the other things you could use ASH for is to investigate I/O consumption. On this occasion, I'm just going to look at the ASH that is single block read in a certain period. So you might have seen that single block read is showing up a lot on top activity in Enterprise Manager. Let's go and see which SQL IDs are consuming that. So I get my top SQL IDs. These are the ones with the highest single block I/O. What kind of single block is it? Well, you can start now to look at the file, the block, the object, and since 11G, the row number. It only works, as I said before, where it's a physical file object, and they will be where P1 is file and P2 is block. So when I first did this, we were speculating that we had a read consistency problem. So the first thing I did is I categorized our table spaces. I said, well, we've got system, we've got undo, we've got a bunch of index table spaces, and everything else is a table space. And I'll join this temporary table to my ASH data. Like that. And now I'll get a profile for how much single block I/O is going on which type of table space. Well, when we did this disproved the undo table space speculation. It can't be read consistency because we're not doing much single block I/O from the undo table space. It must be something else. It's table and index utilization. Okay, which table, which index? Let's dig further. So this time I created a temporary table of database objects. I wanted the object number, which could also be an index, could be a partition and a subpartition, but I want the table name associated with it. And now I join that in, and I can see which objects are used. Now I get a profile of single block I/O by objects in my database, and I can start to examine each of them. And we did, we worked our way down from the top. But the interesting one actually I'm going to follow is this one. This is the main payroll result table. And we looked at that and we thought, that's odd. That's higher than we expect for a payroll process. So then we said, well, which processes are using this table? So I'll go for DB file operations on object IDs that are inside this table. This is a composite partition table, by the way, so we have to join all of the subpartitions. And I'll group it by module. We had instrumented our application, so we also had module in our ASH data. And now I get a profile of access of GP result queue by process. Okay, so what do we got there? We got people querying the payroll result table in SQL+. Oh, and there's SQL Developer down there. We did have a conversation about this. We did say that we don't really think that people logging in SQL+ to do production queries is a good idea. Really, they ought to have canned queries and reports. That stats gathering. This was 11G. This is before the new hash-based number of distinct values came in. So we kind of understood that that was where it was. Today, I think that number would be lower. This was a
Just
surprise.
saying, you've got 5 minutes left.
We got 5 minutes. Okay, so this could be the last topic. This was a surprise to us. We didn't expect this holiday management report at the top of the list. Why is this holiday management report doing so much single block IO? This actually started a whole load of analysis and led to some significant design changes, and we introduced some reporting tables to avoid doing this. So ASH led us to something that we didn't really expect, and it made us do something different. It was an unexpected result. Okay. So we haven't got any questions at the moment. I will do one last subject and then we'll call it a day, because I want to talk about TEMP-SPACE and PGA, and we may not get to do it in as much detail as we'd like. There are 2 columns on the ASH data, TEMP-SPACE allocated and PGA allocated. The manual says TEMP-SPACE is in memory. I think it includes physical temporary space usage. Well, first time I got involved in this, somebody said to me, we've got this financials process. We run 4 versions of this process concurrently, and every night 2 of them succeed and 2 of them fail, and it's never the same 2 twice. What's going on? And they all fail with this unable to extend temp segment. And rather than simply extend the temporary segment, we said, well, let's find out what's consuming it. So you can look at the ASH data, and you can now start to say, well, for each SQL ID, for each plan hash value and module, how much temp space does it use? And so we said, what's the maximum amount of memory that each SQL ID uses? And we got a profile, and we picked out these 2, one SQL statement with 2 different execution plans, and there's 4 process instances in the application out on the right. That's again coming out of the application instrumentation in module and action. And we could see at the time, these statements were both gobbling 132 megabytes, and back then, on this database, that was enough to fill the temporary table space. So you get a handle on what goes on with temporary usage. Here's another example. Here's a more complex SQL statement, and you can see the estimated temp usage in the plan, and it estimates how much memory will actually be used. So if OMEM is if it's done in a single pass, 1 mem means if it's done in 1 pass, 1 to read, with 1 read pass and 1 write pass. So basically using temp once. And you may see if it uses temp more frequently. The bracket is the number of times it feeds through temp space. And out on the right, you've got this used temp, which is the actual amount of used temporary table space in the statement. This is done using system statistics. So again, you can say, well, what is the max and average statement temporary usage? And you can start to profile it by statement. And you get a profile like this. And I was looking at a system and saying, well, where is all this temp space coming from? And I picked out a few statements which were worth investigating. We'll dig further into this one. And if I pull out the ASH data just for 1 execution in 1 session for this statement, then you can see how the ASH builds up over time. And you can produce a table. Well, the next thing I did was I dropped it into Excel. And I can see graphically, here's the behavior of the statement. You can see there's a ramp up phase here on the left. While the temp space is being used, there are actually 2 sort operations going on. And when the first one finishes, it releases space, but the second one is still there, and the data is going to be fetched out of it. Notice that there are gaps in that flat line where the session is idle. It's idle because the client side is busy. It's fetching the data and ingesting the data from the database into the app server. Now, what this means is you cannot simply add up temp space across the database because you will miss the idle sessions. But notice when the ramp up phase, all of the samples, there are no gaps in the sample. So I can do a bit of linear interpolation between my samples, and I can estimate the total amount of space. I'm going to build a temporary table using my rounding function again. And then I'm going to work through all of my ASH data and say for all of the samples that fall in here, where I've got temporary space in use, I'm going to build up a running total of temp space for all of my ASH sample, whether I've got an actual, including the gaps. And then I can say what's going on in my database. So the pale color at the back is the total database activity. And then you've got these sort of reddy orange spots, which are the temp space. And you've also got the PGA. So you can see that they were using about 25 gigs of temp space up front. And then they stopped doing something for a week while they tried to fix it. And then they went back to using it, having allocated more memory. And by the end, they were needing 60 to 70 gig of temp space. So you can get a handle on how much temp space is being used and who is using it. And then you can work on doing something about it. So you can use ASH to find out what's going on. Right, we are not going to get to do index time today, usage today, but the slides are in the presentation. I'm going to have to draw it to a close. Hopefully I've showed you some ideas for how you can dig into the ASH data. Mainly it's about profiling response time, but there's lots more. Be imaginative, go and query this stuff. It will tell you things that you otherwise didn't know, and it may contradict some of your guesses. That's good. Application instrumentation is fundamentally important. It gives you application context, so you know where your SQL comes from. And be aware of the consequences of sampling, because sometimes it can mislead you, and there are some traps you can fall into.
So yeah, we're out of time, but there is no questions. Thank you very much, David.
Okay, thank you very much. Well,
Excellent.
if you have any questions, feel free to contact me offline directly. Happy to talk.
Thank you, David.